Woo! Hey! Are we on? Hey, everybody. Welcome to DroidCon 2025. My name is Tim Hebel. I'm a droid designer of some. Move my mic up. Check 1, 2. How's that? Can y'all hear?
I'll get you. Give me a second.
Test, test, test. Check it, check it. 1, 2. All right. That sounds good. Can we hear? All right. So for today's festivities, welcome to DroidCon. Here's what we're going to talk about. Who am I? How did I get here? A little short story just for context in case you don't know who I am. Then we're going to talk about CADing for metal. And then we'll talk about a few resources, and I'll open up for questions. So check your Yelp reviews. So I started building droids back in 2018. 25 years in the Air Force. I'm currently flying for United Airlines. No affiliation with either of those two organizations, but I've got no business building and creating and designing droids. I have no background in it at all. And I say that because if you are a mechanical engineer and the stuff I'm saying up here doesn't make sense, that's not my fault. But in the same breath, my message there is if you put your nose to the grindstone, you can learn the essential tools necessary to create your own designs. Don't be intimidated by the fact that you don't know how to do it. When I go to schools, I have 3 messages. I'm curious, I'm not afraid to make mistakes, and I don't give up. So if you apply those 3 facilities to droid building, you can get where you want to go. And the last one is the most important, don't give up. So try, fail, learn, move forward, ask questions. There's a great community out there to support this, and that's produced me here today as a non-expert talking as an expert. So, so a little bit about my history in droid building. When I started with 3D printed droids. I was a plastic guy, 100% plastic. And why? Because it was accessible and easy to do. I built R2-D2, the gateway drug to droid building. I took them out to a convention, and it was so much fun that my wife was intending to go to seminars and shopping and all the things you do at conventions, and she couldn't stop watching. And on the way home, she said, next year I want my own droid. So next year we built, 2019, built R5-D4, took it to the convention, and then my daughter, who's sitting back there, would steal one of our droids, disappear for hours. So we built Chopper, and then we're having a moment back there. And we built Chopper, and along the way, I started doing more and more internal work on the droids, designing components, et cetera, et cetera. And then in 2021, I decided, what if I could build my own droid? So I built Arduo, and then after immediately finishing Arduo, I was invited to help build and design version 1 of B2 Emo. And that's where I took on a third of the project, which I thought was the easiest, just the drive section. And it turned out to be the hardest, at least for me. So the history of that aside, as I got deeper into it, I realized, why am I just a plastic guy? I've limited myself unnecessarily to a single medium. So if you take away nothing else in this presentation, use what's available to you and use the right material or tools for the job if you have access to them. And I know that there's a cost differential that can preclude you, but just a little bit of metal in the right places can go a long way to making your plastic droid a powerhouse that can withstand the tests of a con. So I'm not sponsored by anybody. I'm not selling anything. I will mention products and services, but those are the ones that I use because I found out about them. There may be better ones out there. There may be worse ones out there, but these are the ones I use. So that's kind of the intro. So here's what we're going to talk about in the different phases of this. We got setting up your CAD, and this is all going to be Fusion-centric, which is a very popular but not the only CAD software out there, SolidWorks. I'm sure there's analogs in that software that will apply to what I'm talking about, but some clearance factors that differ from plastic designs or any other material in manufacturing. Talk about making the most bang for your buck by making your parts extensible and reusable in different parts of your design, different characteristics of what parts you can actually make in metal, when should you tap or through hole, and just a little bit of different, what types of metal should you use or can you use. And so that's kind of the overview of this next phase here. All right, so CAD setup for Fusion. So I'll bring up Fusion here in a second, but I can't stress most important thing you want to do is make sure you're referencing the right thing. And so when I start one of these designs, I have a master, this is the middle of everything. When I mirror, and you will mirror because there's a natural symmetry to metal. It's by definition symmetrical. So when you build something like this, this exact same part is the exact same part over here. Literally, you just build from the other side of it. So all your designs are, you just designing one half of it, and then you mirror it for the other half. And make sure that plane is the same one every time, because you may end up, if you end up with bad. So I also recommend, and I'll show this in a second, setting up parameters. So when I build, I have chosen my metal thickness, and then I make that a parameter. So when I go to extrude that part, I type in AL for aluminum, and it comes up to 3.175 millimeters every time. That way I'm not making some of them different thicknesses, and you just, again, you're trying to trap your errors in the initial setup. Do the same thing for holes. There's hole tools and everything, but make that a parameter so when you put that M4 screw in there, you don't have to like, what's the size of that M4 screw again? Or the tapped M4 screw? Is this like a Finding Nemo? All right. So the other thing you can do to give yourself an immense head start is download all the CAD for any commercial parts you may be adding to this. So what I'm talking about there is I use GoBuilda parts to help streamline the assembly process. And they have CAD for every one of their parts. Download those, put them in a library on your computer so you can just pull those into your design at will and not have to go searching for them. Let's see. You learn to use the timeline, and we'll talk about that here in a second. But there's two basic modes of modeling in Fusion. One of them is direct modeling, where you just cut and extrude and just go hog wild, and after a long time you end up with the shape you want, and shazam. The other way is to use a timeline where you start off with a drawing and it doesn't extrude, and you can go back and reference those things, and if you change your mind, you can change those things, and it's very powerful, but if you're not managing the timeline, you'll end up with a big, giant, twisty mess with a lot of errors in it. But that process takes time to learn. Do it, because at the end of the day, I used to never use a timeline. Now I can't imagine not using the timeline, just because it gives me so much more power in the, I need to go back to this step and fix it without having to re-drill all those holes, and just you click it and whoop, it fixes itself. And you can also do that with the parameters as part of your build. So with that, let me pull up my Fusion screen. Yes?
Could you go to the component placement one?
Yes, that's exactly what I'm going to talk about. So if you can switch over, let's make sure that's on. There we go. Yeah.
There you go.
So the component placement is there's multiple ways of putting stuff in space in Fusion in particular. And one of them is a joint. Another way is to just simply move it. And the third way is edit the initial position. And of all three, that's the most powerful. Because when you move something, it creates a move event in the timeline. And then if you subsequently move it again, it creates another move event. And then if you throw a joint on it, that'll capture a position. And next thing you know, that thing is locked down, and you don't know how it got locked, and you can't move it. And the way you avoid all that mess, and I'll demonstrate here since we're on that question. So I'll click on this, go build a bar, and I will go to find in browser, and then here it is. And this is a new feature that didn't exist, and when I found out about it, it changed my life in the workflow for Fusion. So I right-click on it, and I go to Edit Initial Position. And what it does is it brings up this Move Position dialog, and what I can do is move this piece and use all my alignment commands to line it up exactly where I want it to go. And then when I hit OK, that's where, when it loads in, that's where it expects it's supposed to be in space, where any other way of getting it there is malleable and rife with chance for errors. And I would spend many iterations moving these bars so they're all perfectly lined up with each other. And I'll just demonstrate a quick move here. So what you do is you're going to set your pivot point. You're going to set what part of the geometry that you want to focus on. In this case, let's focus on this corner here. Come back and hit the check mark. And now when I slide this around, it's in relationship to that corner. And if I want that corner to be perfectly lined up with this face, I got a little dialog box there. Let me just go back. I had that little miss. So if I wanted to line up with, why is it not lining up? Usually, well, I'll just pick another face since it's not playing. It snaps to that face. And when you do it this way, you can take your first block and you stack them into space and make sure that the holes line up. And you basically, you don't want close to being right, you want exactly right. And you have to be meticulous about that. And the magic of the timeline is if I get one wrong or I change my mind of where that piece is supposed to go, I go back to Edit Initial Position. It kind of automatically rolls the timeline back to when that part was first inserted, and you change it. And sometimes you may like, oh, I need to base it on a part that I put in later. You can drag when you insert that part in the timeline back before the other one, as long as there's not a relationship locking them. You can just slide those parts around until you can build a competent structure. So we'll kind of go back over what I was talking about in the parameters and the symmetry, and I'll kind of demonstrate that, and then we'll move on to the next part. So for your master mirror plane, if you're savvy enough to start your project in such a way that you can use the origin, that's the best one because it's the origin. And I recommend using that. A lot of people fall into the trap of building their project off of the origin without relation. Like if you're not thinking about this is all going to be mirrored, you build it in a place and build it like half the distance away from where you think it should be. And again, if you need to change it, Edit Initial Position, move all those things into the right spot, and that gives you a good solid foundation which you can build the rest of your design off of. So parameters, if you go to the Modify and go to Change Parameters, you can set way too many parameters, but I've got just two as an example here. I've got aluminum, and I've got my M4 tap size, because as we'll see later, what clearance is used for different bolt holes and bolt sizes. You can, the tapped ones are the critical ones, because that's the size you want that you're going to tap when you want to screw a bolt into a piece of metal and not to have another nut on the other side. And anytime you can use a tap in your design, that's great, because you don't have to have another component in your design to catch the other side of that screw. And that can really streamline your parts and your build if you make the metal plate do the work of that fastener for you. It has limits. You can't over torque it. You can strip it out and all those things. But if you use that, it will help you in the long run. And then we talked about plate thickness. So let's say for example, I wanted to make this an aluminum plate. So any sketch will do, but you can also go off a surface. I hit the extrude key, and then for distance, I'm going to type AL. And you can see it automatically populates, or maybe you can't see, yeah, 3.175. So that will, in that easy step, because 3.175 is kind of hard to type, and sometimes you might type 3.715, you might type 125, which is an eighth of an inch, or whatever I'm saying. It's easy to make that number wrong when you're typing it thousands of times. So put it as a parameter and lock it in with the right value, and that will save you a lot of work in the long run, because most of CAD is error trapping and correction. This is becoming a good meme. He doesn't have that sound. Is he really?
There's definitely Bluetooth interference going on because Steve made that same sound and he doesn't have it.
Yeah, he doesn't have that sound.
We got the same
There's a plug. Just unplug B from the Arduino from the wall. He will go silent. That's crazy. My droid has been infected by the dark side. All right, so what else we need to talk about? Component placement. So in this design, what I did is I created components. So you have a regular body, which is just a 3D shape, but a component is a body and all of its baggage. Like it has its own origin. Oh, I thought. So it has its own origin. It has all the other things that a project has, but it's all in a component. And what a component can have is other components nested in it. So in this build, you notice I have my go build a component, and when I brought these parts, these CAD parts in, what I did is I activated this component. And why can't I activate the component? What mode am I in?
Which version of CAD are you using? The free version or?
I pay for the subscription only because I write software as another alter ego, and if somebody does something that I like and I want to support, I pay for it. I pay for like the $300 a year version of it or whatever. Nothing that I'm using is any of the pro feature. I don't use any of the pay for features. Like I don't really work with other people. Not that I don't want to work with other people, but I'm not using any of the team stuff, and I don't think I'm using any of the features that aren't available in the free version. So yes, I pay for it, but no, I'm not doing anything magic or not available to the public in a free version. So I'm in some mode. Normally what you do is you right click, you click this and a little dot shows up. I don't know. It's one of those, like here's the dot I'm looking for, but that's irrelevant. Basically you activate the component, and anytime you bring that active component in, all those components will come into that active component versus the main project. So the byproduct of this, oh, there it is. There's a little dot. Why can't I click it? It keeps going away. It doesn't like me. Anyway, what I was trying to show is you can grab those and treat them all as a single unit. So once you're done figuring out where those parts go, you can hide them when you're working on other aspects of your design if you group them reasonably. All right, so you can see in my timeline, I've got, one more thing about the timeline and the components. Each component has its own timeline chunk. So if I go to the master project, I've got 400 lines in the whole project. But if I select an active component, that list, it's still the same list, but it's just a subset of what applies to that component. So it makes managing components way easier in the timeline when you work on a component level of design. And you can, again, components can have subcomponents. So when you're drilling down to work on just that one little doohickey, activate it, and then this timeline will be like 5 or 6 or 8 cells versus a 25 or 40 where it's easy to get lost in. So that's kind of a pro tip on how to manage your timeline, is to work at the component level. And the mistake is forgetting to activate the component, and that step now falls in the master timeline, and that can make things tricky. But the other thing with a timeline, anytime you find a little yellow or red, don't ignore it. Find out why. Usually what's going on is it's a sketch that was constrained inappropriately, and you moved something or deleted something that sketch was trying to find, and now it's complaining. It caches it. It knows what you did before, but it doesn't know what happened to its information. So you basically lost your ability to do parametric timeline-based functions when you have a little error or fault in there. Sometimes you can complete the project, but if you're going to learn to use the timeline, troubleshoot all those errors, and it will tell you what it's complaining about. And you can actually go in a sketch, and it'll say restore lost references, and you can click and regenerate them all. But don't ignore those warnings, otherwise you will be in timeline hell, and you'll curse me for suggesting even using it. Let's see. We can switch back to the iPad. Okay, so other things to consider for designing in metal, and specifically metal plates. Clearances. Lasers are accurate. If you want a 4mm hole, you draw a 4mm hole and it comes out 4mm, and so that will automatically fit an M4 bolt. Easy peasy, because it requires a form, and it's like magic. Well, when I was dealing with plastic, if I wanted a 4mm hole, I had to make it a 4.2mm hole or 4.3, depending on the nozzle size, and or how bad my printer was or how good my printer was. So it was very much dependent on where this part was going and what it was designed for. Whereas when I'm dealing with metal, it's going to be the size you expected it within machine tolerances. And so that's an actual joy, a burden lifted off. You can design with zero clearance. If you want this plate 125mm from this plate, you don't have to put in a little fudge factor for them joining together like you do in plastic, like 0.2mm or whatever. It just joins and fits. So how do you know how to make your threaded holes or your tapped holes? There's a simple formula for metric, and I rue anybody who doesn't use metric for design. I know there's a lot of Imperial stuff at Ace Hardware that you can buy, but please make your life easier. Use metric in designs. It's much more simple to comprehend. You know, which is bigger, 5/32 or 19/24? You can probably figure that one out. But I know M3 is smaller than M4. So it's a simple formula. You take the size of the bolt and you minus the pitch thread, and that's the size of the hole. That's the caveman way of doing it. There's other formulas to create, like 3.332 or what is the actual one. But this is perfectly fine for what we're doing in the design. If you just want to quick and dirty capture all your M4, M5, M2, whatever size of the design, and put those in as parameters, so you can quickly, as you're going through your design, just set all those hole sizes. Let's see. One thing that's important is in metal plates, we're not building a 3D structure. We're basically building a 2D structure that we're going to make into a 3D structure with something else. The something else could be another plate. Or it could be a 3D printed box that we're going to capture with metal plates. Whatever it is, I chose in this design to use the Go Builda bars. They're 8mm by 8mm with every 8mm holes, and the ends are tapped. So they're perfect for building a box out of metal. And they come in all kinds of sizes. And there's two ways of doing it. One is to take stock parts and build around that. That's what I chose to do. The other is to take apart, and if it's not quite right, cut it. I just don't like that, because those cuts are going to be inaccurate, and you have to it's just find the magic part in that 8mm catalog, and it might be 80mm is the perfect size to capture my motor give it clearance, and have it sit. So there's a little bit of sleuthing required, but the message is try to take a stock part and do all the heavy lifting. Somebody else has designed that, and it's commercially off the shelf. You don't have to do that yourself. You can, but what we're looking for, back to the accuracy thing, everything has to line up perfectly, and we have the platform to have everything line up perfectly, but as the designer, we can't just like, oh, that's close enough. When I position things, I'm typing the decimal points, or I'm having it auto perfectly line up using the align commands when I'm moving the components. Don't just go in there and freelance it, because it's going to cause you untold troubles and errors, and things just won't line up and you can't assemble it. If you take your time, when you go put it together, it will go together very easily. You're like, oh, like all the holes line up, and it's a magic experience that's different from coming from the 3D printed world, where it didn't quite print and there's a little twist to it, and you kind of forcing the screws. None of that happens here. It just goes together because you do your homework. Let's see here. So now that we've designed some parts, we'll talk a little bit about the kind of the constraints. So I mentioned symmetry a few times. Symmetry, by nature, this is a symmetrical part because it's really, although it's a 3D part because it's got thickness, it's a 2D shape that is symmetrical in a certain plane, sometimes all orientations, but you can use that to your advantage in that when you go to manufacture a part, it costs them a setup fee, and it may cost $40 to make this plate. But if you make 2 of them, it might be $37. If you make 4 of them, they might be $27. So the price drops precipitously as you add an iteration, a duplicate of that part. Because once I got the machine set up to run it, now you're paying for machine runtime and the raw material. You're not paying for the setup. And the setup is involved in every part. They have to do the setup. So take advantage of that, and you may end up adding extra holes that you don't need on one side because it's the same part as the other side with the mounting holes. And it's cheaper to buy 2 plates that are the same, and one has extra holes that don't impact the strength or whatever. And then now you buy 8 of those, which the price drops really low, instead of having 2 sets of 4 and another 2 sets of 4. You can even extend that if you have a mature design and buy with your buddy, because if you need 4 and he needs 4 and they need 4, you can buy 12 and the price is cheaper for everybody. But I don't recommend doing that if you're prototyping, because you're going to have to replace some parts. But the other nice thing about part replacement is, since you have a nice sturdy material, you can actually modify it as long as you're not needing to take or to add, you can always take away. You can drill holes that you missed or whatever. But you can't make that M3 tap that you stripped out get smaller. So part of your hole patterns, keep them symmetrical. So an example of that is the plate. Let me see if I can pull up further down. I'll just go to the end of the timeline. So this plate here, yes, please. So here is the end of B2, and I've got this little plate here, and that plate appears on 4 different places. And to make my symmetry work, these plates are also, you don't want to just have your holes just randomly placed. They work, but when you flip it around, you want it to be symmetrical on the other side. So don't just randomly throw this much clearance from here to here, this hole spacing. When you design that sketch, constrain how far it is away from the edge. And we'll talk a little bit about how close you can get to the edge, and that's depending on the manufacturer, what they can do for you. And then make sure that the other hole is that far from the edge, so when you flip it, you truly have symmetry available to you in your build. Let's see what else we got here. Sketch constraints. Here's a fun fact. When you're in Fusion, if your sketch is fully constrained, all the lines are black. If it's not constrained, it's blue. So if you look at your sketch and it's all the lines are blue, you're not done. If you can, when you're done with that sketch, it's all black. Meaning that when I change my mind later and I decide I'm going to use, say, an M5 screw, that distance will automatically or programmatically be still correct with the M5 screw because the sketch was constrained. If not, that hole can float. Or worse, you move. So have fully constrained sketches. It's kind of a, I don't say an art form, but it's not sometimes easy to do just because you think you're constraining it and you're not. There's a auto constrain using AI that Fusion has added. I've never played with it, but if you're having troubles, maybe that'll help. I don't know. So there's limits to what metal can do. They can only make it so thin, and they can only cut so close to the edge. All those will be on the manufacturer's website. I'll show you in a minute SendCutSend's design criteria. It's based on the material you're using and the thickness and all those things. They've got a little spreadsheet or blog that tells you all those things. But take a look at that first so you're not creating things that are unmakeable. All right, so let's go back to the iPad. So the other thing that is coming from a plastic designer is I could make any shape I wanted to. It could be as complicated. It could be in 3 dimensions. It could print with or without supports. I could make these really complicated shapes. When you're doing metal plates, your shapes are not complicated. And you got to keep that symmetry in mind and keep the fact that when you want to go 3D, you can either build on it with screw-on components or 2020 extrusion or 2040 extrusion or whatever. But you really can't make that little extra tab to hold up, to screw something onto, or can you? There's ways to create files that are bendable. You can create a metal box, and Fusion has tools for sheet metal bending, and the parameters to do that are on the website, the bend angles and the tolerances and all that. But I avoided all the bending metal stuff for 2 reasons. Reason 1, it's a softer, more flexible metal, and I'm building something rigid. So I don't want a bendable metal. And 2, when they bend it, or you bend it, if you get it twisted a little bit, your box isn't going to go together. So you may be tempted to just, hey, I'll just make tabs that bend up, and you screw in, have them tapped, and I can just have it built that way. Yeah, but you're going to make sacrifices in the precision and the assemblability of that project. So I didn't do any bendy parts. Twisting is the enemy. So what I mean by that is when you're building out your structures, I imagine I'm building something out of paper mache and then stepping on it. Like, where do you think it's going to break? And really just, I don't have any formulas I'm using, although you can think of the old lever, the fulcrum. The further you are away, the more that same force is going to impact where it's going to break. So kind of keep in mind how far apart, and particularly in this design, this whole wheel is hanging off a single point. So it's continually wanting to twist and turn as I drive. And so this joint here has to be hella strong, because otherwise it's going to fail, that right there. So imagine when you were a little kid making stuff out of paper mache and how they would eventually broke as you played with them. Think of that fragileness. Even though you're building something robust and really tough, make sure you're putting the toughness in all the spots where it's going to get into trouble. And you'll learn whether you get into trouble when you operate it, but if you can imagine how it's going to cause you trouble when you're building it, that'll save you some time down the road. When in doubt, make it stronger. That's like the 1950s look of mechanical engineering. How strong do we make it? Hella strong. And It may be more expensive. You may be able to optimize it, but until you get or are a real engineer and doing the math, that's how my design approach was. All right, so anchor it in multiple parts so you can see. Let's split back to Fusion, please. So in this design, I start off with this metal base, a box that runs the length of the droid, and I wanted to control and hold on to these wheels in that box. And then as I finish that project, like, well, now I need to go up. And as I go up, my lever gets bigger, and my twisting forces get bigger because now I'm acting on the base further away from it. So I grab that plate here and here and here. And so I've got the corner of my box is all secure. And then as I go up, I grab onto it 4 more times so that part can't sway. And then I go around the corner and kind of do the same thing. So think in reinforcing in 3 dimensions since you don't have a unibody plastic structure that can do that for you. And if you can optimize it, but I like to grab onto things at least 4 times, just in general. Sometimes there's no space for it. Sometimes you can only do 2, sometimes or 3. If you're only doing 1, I would say you need to rethink it a little bit. If you're only grabbing that, because they can pivot and so strap everything down as best you can. All right, back to the iPad. All right, optimize your designs. Even though it seems complex, simple is best. If you can use a single part to span and do 2 jobs for you, like I've done in that last example with that plate, do that and try to keep things simple. That's a tall order, hard to do. It's easy to get tangled, but anytime you just kind of, like most of my design work is not clicking the mouse or typing. It's just staring at it and going, what? Just mull it over. It takes time to really understand the impact of your design, understand what is the simplest shape that will do the job I'm trying to do. And just like in your mind, imagine a bunch of those before you even start clicking on anything, and then start clicking on stuff and trying it out, is what I would recommend. Use 90-degree angles, because basically when we're doing metal, it's naturally got that symmetry and naturally wants to be 90 degrees to each other. If you're doing something more complicated, now so must your designs be more complicated, because now you might need to add half corners around it, and your parts count goes up, your design goes up, your complexity. I would look at this as mostly structural stuff, and I'm going to skin it with other materials, plastics or whatever. So at the heart of it, I want kind of boxes that I can build, and boxes are easy to build because there's a lot of 90-degree stock out there. If that won't work for you, sometimes you have to go 45 degrees or 30, but that just complicates your life. If you can avoid not using complex angles, I would recommend it. And another fun thing is you can, back to my core design principle, you don't have to use all metal. So I designed these motor mount boxes as these really strong, rigid metal boxes with all the bars inside, and they're all lined up perfectly. And I let Brian Dodds build my design before it was done. He goes, Tim, you can just put a 3D printed core in there, slap the metal plates on it, it's just as strong. You're not going to be able to break it. It's going to be just as, like, you're right. I got locked into my own trying to unlock myself trap of getting away from plastic when, I could save a lot of money because I 1, 2, 3, 4, 6, 12 plates I didn't have to buy. I could just 3D print a metal box. And even with this design, there's a 3D printed part in there to act as kind of a wheel well, so I don't get junk and beer and stuff inside the motor. So I have a 3D printed wheel well, but it's in a fully metal box, and I could have done, keeping it simple, both of those tasks with a single 3D printed core and the same metal structure. So that's kind of the optimized design. Use the right material, the right tools. So tap hole versus through hole. I'll show you a couple of designs, like I'll upload one to their website just to kind of show you the interface. But you really, really, really have to pay attention to your hole sizes, and it's super easy to screw it up. You will find missing holes. You will find wrong size holes, unneeded holes, misplaced holes. So I recommend print all these parts out and put it together, and you'll find, because in CAD, I can have a bolt through a solid surface, and it's not going to complain, and it's going to look perfect. It's right where it should be. And when you print it out, like, oh, I never drilled that hole. I never cut that hole. It got missed in that step. So you can roll your timeline back, include that hole in the cut, and then you're fixed. Whereas, so use the timeline. But definitely prototype I even 3D printed the 2020 extrusions. Because you can really, it will really inform you as to how it goes together. You get one practice build out of it. And you also get the advantage of, oh, I can't even put this together. I can't get the screwdriver or the bolt driver in there, or there's physically, it's constrained by its own build. So you'll find those things, because CAD's very evil. It won't tell you when you're making a big mistake and you can't assemble the thing you just created. So before you ever send it off to get cut in metal, print it out. If you don't have a printer, they're $300.
How do you manage tolerances, right? You just talked about designing everything to metal. Those need basically no tolerance, and then you go print in plastic.
Well, I will take that into account, that it may not go together perfectly, but really those errors I had, that's what I'm trapping, the assemblability of it, and are the holes approximately in the right place. I don't expect it to be structural or usable, or it's just really, it's an assembly exercise. And that assembly informs you how to go together, order of operations, missing, lost holes, or other, like you may need an extra wide cutout because when you build it, you need a little that to put the parts in.
So you use common sense.
Yeah, I just, because keeping it simple, I just want that overall, it's a gross error check before you spend a actual check. All right, so a little bit about some nuts and bolts. I know I'm running probably too long. 15 minutes, so I'll wrap this up. So 5052 is that bendable metal, and the rigid 6061, that's what this is all. It's a nice kind of firm metal that has good strength and flex capabilities. And then kind of the uber aluminum is 7075. These gears are milled in 7075. And I haven't talked about CNC milling or any of that, but you can also do those things. You can now design in 3D, but that's a whole different topic. So this is the super tough, mid-grade, strong enough, bendable. Maybe you can use it. I avoid it. And I used the 1/8 inch aluminum for all this. You can tap it effectively. I mean, you can't torque it down, but you can tap and tighten those types of that grade of aluminum at 1/8 of an inch. You can also go to 1/4 inch and thicker. So depending on what you're building and how strong it needs to be, you can use titanium if you want, or fiberglass, or what do you call it, carbon fiber, all kinds of materials that you can have this process done. I just applied it to 1/8 inch aluminum metal as kind of a framework of where I started this journey. And it literally can take you anywhere, but I just want to kind of boop, constrain it. Notice that? Boop, beep. So resources, SendCutSend is a place in the States where you can upload a DXF, which is just a 2D drawing, or a step file, 3D file, which I recommend doing just because it auto imports your thickness, so you don't end up with clicking on the wrong button and getting the wrong size part. GoBuilda, they've got this catalog of these perfectly, almost purpose-built products of these little aluminum bars that really make your life easy, because you know, oh, I can just do that, have a through hole, tap into the end, and you can. It's built for making boxes. PCBWay, will also do this type of manufacturing and doing gears and geometry. That's kind of like the US version of that. It's kind of a clearinghouse for these ad hoc on-call production services at varying prices. And I didn't have any problems with quality from anybody I used. So it really comes down to price and time frame as to who you choose, I think. But there may be other people who have other experiences.
Question.
Yes,
Have you run into any problems when they find out what you're building, the price goes up?
I haven't.
When did they find out we're building droids and stuff, the price starts to go up?
Well, I haven't seen
What
that.
was that question again? I'm
Oh,
sorry.
the
I don't have a
question-
microphone.
Yes, I'm sorry.
Stuff like that.
No, he needs to repeat it
Yeah,
because
I'll
no one
repeat the
online can
question.
hear.
So the question is, have I had any problems with when they find out I'm building a droid, they jack up the prices? The experience is I have not, and I haven't communicated with them what this is for. I just say, I need this widget, and they go, we get it by Wednesday. And that's kind of the beauty of SendCutSend is their quick turnaround time. I've seen it. I was Sunday night at 2 o'clock in the morning. I was in California. I got to get this part finished. Finally finished it, uploaded it, and 2 minutes later, I get an email, in production. All right, cool. And I got the part when I got home from my trip. So that's kind of the magic of it. You don't have to have a CNC machine or a milling machine or a laser cutting machine because it's almost like ordering it off of Amazon. Obviously, the more complex the order and but they can really quickly turn around stuff. So when you're ordering a part, you're going to get a list of upsells. And the one I recommend highly, it's a small fee, maybe $1 a part or whatever, get the deburring. I chose to cheap out on my first order and regretted it because now you have to buy a deburring tool and a file. And it's just the prep work to get that where they could have done it for almost free. I mean, in my time, $1 per piece is free. Just keep the deburring. There's limits on how small the part can be to get deburred, but they're going to come with a little sharpish edge from where the laser hit it. And if you don't have them cut that off, you have to do it. Countersinking. I chose 0 countersinking because I have a little countersink bit and it works great and I can make them all perfect because all the screws are a little bit different. So I didn't choose any countersinking. If you don't like countersinking or you're scared of your ability not to drill all the way through, you can buy that. Powder coating, if you want to make it fancy, or anodizing. Like these gears are anodized in orange just because I thought, you know what? I'm spending a lot of money. What's another $50? And it'll look really cool. So, but both of those actually protect your metal. So for corrosion and other things. So there's reasons to do it other than aesthetics. But particularly when you're in a place where people are going to look at your work, normally at a convention, they don't see your work, but when you do in show and tell, it's really cool. Go ahead.
Do you have to adjust the tolerances for the powder coating?
I didn't do any powder coating, and I imagine you would if you had a super tight clearances, but it's almost imperceptible. It's not that thick. So I didn't do anything for, like, these are anodized, and they work just as if they weren't anodized. It's a really, really thin powder they put on it. Tapping. This is one where you're going to have to budget your own confidence in tapping good holes or paying for extra. Hello. You have a question?
Yeah. Have you ever tried with your drawing? Have you ever tried prototyping with cardboard or something?
Yeah, for prototyping, I have a 3D printer. That's where my life began. So I prototype everything. I print it out first. You could certainly prototype in cardboard if that's, but what you end up there is you're creating the cardboard unless you have like a Cricut machine that can cut the cardboard based on your specifications. You're inducing one more layer of, you could make a mistake in your prototype because it doesn't perfectly match the CAD, where 3D printing will match the CAD. So if you don't have access to a 3D printer, you could do that, but I don't know that you're going to get your bang for your buck out of that necessarily. Although you could do the assemblability stuff. So tapping, I have in this design mission critical taps. Those are the ones that define the squareness of the box, and I wanted those to be perfectly machine built so that that hole wasn't at an angle, it wasn't cut out. So taps are expensive. You can take a $30 plate of metal, add 15 taps to it, and now it's a $75 plate of metal. So it's something that you want to use judiciously. If you're happy tapping your own stuff and you're a power tapper, you have one of those cool little tools that you can use your drill press to tap it, knock yourself out, you can save a lot of money. And plus, you won't get wrongly tapped holes. Yes?
So what decision do you use between doing tapping and just a hole through?
So in the design, if I can bolt onto a plate with taps, and I know there's, like I'm bolting a component, like there's, you can't see it here, but there's a slider or a rail that I want to bolt to my plate. I want those holes to be tapped because I don't want to get behind it and try to put a nut on the other side of that. If I'm building a box and I know I'm going into go build a beam that's already tapped on the end, that's a through hole. And the good news is if you get a small hole that should be through hole, take out your M4 drill, zoop, it's a through hole. If you get it wrong the other way, you're trying to put a bolt on it or a nut on the other side of it. Yeah, now it's an M5. Anyway, so you got tumbling, and they can also do hardware mounting. They can mount nuts and parts onto your, and really it comes down to your budget and your timeline, because all these things take more time to produce. So, but those features are there, upsell. Once you get into the habit of going there and you kind of know how much you're going to spend, and you know, I really want them to do this for me, just click. But that's kind of your option. So we're kind of running short on time, so I'm not going to do a live demo. I'm available to discuss. What did I miss?
Parameters on Fusion, is there a way to globally set those for any file or both of them?
I think there is, and I've had that thought. So the question is, can you globally set your parameters? And I believe there's a way to import them, where you make a master set of parameters and import them as a starting point of your file. I've never done that just because I usually remember to do that when it's kind of too late. And so I don't have a master list. I want to develop that. I haven't done that yet, but I'm pretty sure you can import parameters as a starting point.
I've seen that there's supposed to be a way to do that. I've seen someone do little B's and C's and stuff, and they have a master set that they have that puts in all their files.
Yeah, so that capability exists, and like I said, I'm not an expert, but that'd be a great idea to do that. Any other questions?
Yeah, Tim, so when you CAD your parts for metal, you mentioned before about the hole sizes and stuff that you have those set up. When you prototype, though, and print out that piece in plastic, is there a way to modify those parameters, or do you just hog out those holes after you print out the part?
You can have, you can go through those parameters, and if you type 4.2 instead of 4, it'll print out with the right, but then you have to go back and undo it. So the shorter answer is I get my M4 drill out and just because I know this isn't a production piece, it's an error checker. So I just take the expedient way and cut the holes. Anything else? Yes.
I feel like we've all been to the restaurant where they expect you to order in a certain way, or else they don't want your business, or they send you on. I feel like metal suppliers and other industrial supply type situations can be similar. If you run into anything where you're ordering a part and you give your DXF and you give it to them, like as a 3D printing person who can just do it all in your house versus oh, I'm interfacing with
A third party.
a third party that's used to doing it a certain way. Are there any gotchas that you've encountered?
Yeah, so the way you mitigate the gotchas, and we really don't have the time, but if you go to the SendCutSend website, you pick a material and you say, I want the whatever grade of aluminum, 6061 aluminum, it will have a spec sheet saying, here's how close you can get to the edge, here's the minimum width, here's the maximum size, here's the minimum size, and if you abide by all of their manufacturing constraints, I got no pushback. If you get close on one, they will contact you and say, hey, this part here, And Dave Ferrara was telling me how they worked with him. Like, hey, if you did this, we could do that. Like, hey, make that, and then we'll cut it in half, and then we'll get what you want. So there's ways to work around it, and as you get more familiar with it, you earn those ways as part of your bag of tricks. But on your first initial out of the gate, look at those guidelines, abide by them, and upload the files. Click, click, click. Choose all the options. Choose all the holes. And like I didn't have any problems of that nature. But if you do find those problems, it's probably because you didn't follow the rules. And those rules are published. So just take a little time up front before while you're in the thinking phase of okay, how do these parts? Because everyone wants their holes right on the edge, and so just if you follow the rules, you'll be fine. Anyone else? All right. Well, thank you for your attention. I hope I didn't say anything that was wrong.
Thank you all. That is lunchtime.
Sure.